Sairam, having seen the study of potassium dichromate as an oxidizing agent, now let us study another compound which is used as an oxidizing agent, which is potassium permanganate. You must have heard of this compound many a times, where this potassium permanganate can also be used to remove the impurities from water compounds which are there. So, if you put this potassium permanganate crystals, some impurities can be attracted towards itself. So, we will first study the preparation of this compound and then let us see what are its uses. But before that, just a small history of this potassium permanganate and what are its applicability. So, we see that this is also a very good oxidizing agent, like the way we had potassium dichromate, and because it is a very good oxidizing agent, it can be used as an oxidant in preparative organic chemistry. Now, what is this preparative organic chemistry? We have many compounds preparation that happen in day-to-day life in the research sector as well as in the industry. So, wherever there is a need of this oxidizing agent, we can use this potassium permanganate for that. So, this has been obtained from the earth's crust by an ore called as pyrolusite ore, which is a combination of manganese with oxygen in that. So, manganese dioxide, this ore can be utilized to obtain the potassium permanganate compound for us. And on a commercial large scale basis, this is mainly by the oxidation of this MnO2 compound, and then when we undertake electrolysis, because we need a change in electron systems, we will get this potassium permanganate. So, for now let us see how do we prepare this compound potassium permanganate. So, the very first step will definitely involve the ore that is present, which is MnO2. Now, we see that there is a fusion of this MnO2 with potassium hydroxide in the presence of air. The O2 there indicates air, and this will give us the compound potassium component itself, but only thing is that compound which is formed is not direct permanganate, but it is a manganate compound, and the byproduct there we generally obtain it to be water. So, this reaction, what it does for us is it involves fusion with a base. Remember the earlier preparation of potassium dichromate, there also a similar process was undertaken, where there it was fusion with sodium carbonate and air. Whereas now here, depending on their properties, we have the fusion with potassium hydroxide and air, and these are the products that are formed here. So, for the case of balancing, once again when we see this, we see that the Mn is same on either sides. Potassium, there is a difference. So, let me take this as 2 KOH for this. So, potassium and Mn are satisfied. What about hydrogen? Hydrogen is also satisfied here. What about oxygen? 2 here, 2 here, 2 here. Whereas on the right hand side, this is 4, but here there is only one oxygen which is present here. So, because we have to balance this oxygen part in these cases, so for the entire balancing system, where because it also will disturb the presence of hydrogen, we will take the trial and error method for balancing, and that is how you will see the first step of equation which is formed there. So, in this equation you see with the respective trial and error methods, where two molecules are being employed. So, basically it is being doubled so that of our initial aspect, so that the overall system is being balanced completely. So, this balancing will give us potassium manganate compound, and once you go to the second step, you realize that they have suddenly gone to the anionic form. Now, why is it that they have gone to that anionic form? Let us just see in this parts now, where MnO4 which is formed here, K2MnO4 which is formed in the first step, basically when you divide it into its ions, you will find it 2K plus and MnO4 2 minus. This is how the ionic aspect of this compound happens. So, once again remember that the role of potassium here is only of a counter ion, whereas this is our main component which is utilized for preparation. So, this formation of ionic compound is the one that is utilized for the second step, and from this we tend to get the permanganate ion. So, this MnO4 minus is called as permanganate ion. This is obtained by treatment with acids. So, once again utilization of H plus indicates that it is an acid, and generally we do consider either hydrochloric acid or sulfuric acid in this case. So, now you may see here that this was the ionic representation which I showed. Here the manganate ion is getting converted into permanganate ion in the presence of H plus. There is once again a formation of MnO2, which means that the purification of the ore also has happened during this process. So, you can take this once again back for further production also. So, that is the advantage of this process. So, what have we got here now is this permanganate ion, and finally this permanganate ion can be reacted with its counter ion, and that is how you are able to form KMnO4 systems which are being present for our regular usages of this compound. So, this is just the theoretical reaction setup which is seen, which are also able to see it in the 3 steps that are being projected in these cases. But what is important here to know is that this conversion of MnO2 minus, the 2 minus condition and 1 minus condition, this conversion involves the electrolytic methods in their conversion parts. Let us also see the structure of these compounds which are there, where both of them are seen to be tetrahedral in nature, but the color of the compound does change. So, what is the color of the compound? The manganate ion is in greenish color. So, at the end of the first step you actually get a green salt. At the end of the second step, where you are able to form the permanganate ion, you are able to get the purple color salt. So, potassium permanganate is purple in color when we generally see, even when we make a solution, we get a purple colored solution in these cases. For our knowledge, we also got to know what are the oxidation states of this compounds: MnO4 2 minus, MnO4 minus. This is the manganate ion, this is the permanganate ion. So, Mn, I do not know its oxidation state. Oxygen, in total there are 4 oxygens. We know the oxidation state to be -2, and what is the overall charge here? It is -2. So, x minus 6 is equal to -2, x is equal to -2 plus 6, I am sorry, this is 8. So, if you see the calculation, 4 into 2, it has to come to 8, and then that 8 I have taken. So, x will be equal to plus 6 charge. So, in this system the manganese ion charge is plus 6, whereas when I consider this, x plus 4 into -2 is equal to -1, x minus 8 is equal to -1, x minus 1 plus 8, whereas here x is plus 7. So, in potassium permanganate, the oxidation state of these manganese will be plus 7. Whereas here it was plus 6. So, this is the conversion that is employed in the electrolytic method to obtain potassium permanganate at the end. So, this is how the overall methodology of preparation happens for potassium permanganate. So, now let us see some of its application and uses in these cases. The very first thing that we see is how this KMnO4 can act as a very good oxidizing agent. Once again, just to rewind the concept of oxidizing agent. Oxidizing agent is somebody who will help in the oxidation of the systems. So, let us see at the very first reaction that has happened. So, the first reaction I have shown about the conversion of iodine ions to iodide systems which are present. So, I minus ions are getting converted into I2. What is happening in this case? The charge on I minus is -1, I2 the charge is bound to be 0. Any compound in its elemental state or stable state will have the oxidation state equal to 0. So, what has happened in this process now? In this process, -1 has got converted to 0, which means that it has lost electrons. Now, that is for one iodine ion, but in total you have 10, 5 into 2 and then 10. So, that is why the total number of electrons that have played here is -10. Now, who has oxidized this? This is oxidation. Losing of electrons is called as oxidation. So, who has helped in this oxidation is nothing but the manganese which is present. So, once again when we see that reaction now, in that case we are able to see a conversion of MnO4 minus getting converted into Mn2 plus state. So, always remember that in acidic conditions manganese will convert itself from +7 state to +2 state. This is the +7 state. We have just now seen the calculation of this. It has converted into +2 state. What do you mean by +7 to +2? +7 indicates 7 electrons shortage. +2 indicates only 2 electron shortage. Now, this is possible if we add 5 electrons to this. This compound had 7 less, this compound had 2 less. So, when this compound got added with 5 electrons, it came equivalent to Mn plus 2 state. So, how do we balance this reaction now? First thing is we have to look at balancing of the electrons. So, therefore, this entire equation let me multiply by 2. This is done so that finally, I tend to get 2 MnO4 minus, I have multiplied this by 2 plus 10 electrons giving rise to 2 Mn2 plus. So, to avoid confusion, what I will do now is, since I have already multiplied this, let me remove that reaction from the system, and now let me look at the complete balancing parts of this. So, what are the complete balancing parts now? 10 iodine ions which are there. Along with that, let me use this 2 MnO4 minus ions. The 10 electrons on either sides get cancelled. So, what is present now on the right hand side is 5I2 plus 2 Mn2 plus. But now, once you see this reaction, you do not see a complete balancing. There is oxygen available here, there are no oxygens available that side, and we always know that in the acidic medium, the balancing has to be done by adding H plus on the left side and H2O on the right side. So, how is this balancing taking place now? So, in this case 10 iodines are satisfied, manganese is satisfied, but oxygen in total here are 8. So, that is why to balance that, let me take this as 8 H2O. In that process this became 16. So, let me take this as 16 H plus. So, once again if you see now the entire reaction, everything seems to be balanced: iodine, manganese, hydrogen, oxygen. So, every single component there is balanced because of such a consideration that we have taken. So, what is the role of manganese here is, it is helping in oxidation, and remember the heading that is shown there, this is an acidic medium only. So, just to explain another example, let me take the conversion of the second example which is present there, where Fe2 plus ion is getting converted into Fe3 plus ion. To say it, ferrous ion is getting converted into ferric ion, and this system is supported by an oxidizing agent which is nothing but potassium permanganate. Potassium is not used here, whereas the permanganate ion is getting converted into manganese ion. So, what is happening here? +2 state to +3 state, which means that it has lost another 1 electron. So, that losing of 1 electron, let me write it here. In this case, the oxidation states have changed from +7 to +2. So, change from +7 to +2 indicates that this has taken 5 electrons to undertake this change, because there is a difference of 5 electrons. Now, when I have to balance the number of electrons, I need to multiply this entire equation by 5. So, when I multiply that, I am going to write it as 5 Fe2 plus giving rise to 5 Fe3 plus 5 electrons. How will I come to the overall reaction now? 5 electrons get cancelled on either sides. So, what all are left over? Let me write them: MnO4 minus plus 5 Fe2 plus gives rise to 5 Fe3 plus Mn2 plus. What are we supposed to do now? Because it is an acid medium, we are going to use H plus and H2O on either side. So, this side I will be using H plus, this side I will be using H2O. The question is, how many H plus, how many H2O? There are in total 4 oxygens available here. So, I will use 4 H2O. Because of this, this has become 8 hydrogen now, therefore, I will use 8 H plus. This is the reaction that you are able to see there. I think similarly on the understanding of these two reactions, I am sure you can try the third reaction also which is there, which is not at all different from these two. Just that instead of iodide ions and iron ions, they have now used nitrate and nitrite ions, where there is a conversion between the two. So if this was in the acidic medium, let us now see the oxidation by KMnO4 in alkaline or basic medium. Let me remind you by our redox reaction chapter that whether it is in acid medium or basic medium, oxidizing property does work there, with a difference that in the basic medium, whenever we balance the reactions, our balancing happens on the left hand side with water and right hand side with the OH minus compound, which is the hydroxide ion which is present. So as an example, let me take this process now where iodide ion is going to be converted into iodate ion, which is IO3 minus. Now the question is, what are the changes in the oxidizing states of the compound? So that factor we need to analyze that now. So what is the charge on iodine present here? It is -1, can be very easily known from whatever is written on the iodine, where it is -1. So what is the charge on this iodine now? That I have to calculate, where iodine, let me take it as X. I have 3 oxygens where the charge of each oxygen is -2, and I also have the overall charge equal to -1. So in this case now, so here X minus 6 will be equal to -1, X will be equal to -1 plus 6, which will be equal to +5. So the charge on this system is now going to be +5. So what has happened here is there is a conversion from -1 state to +5 state in this condition. So similarly here, these are the conditions which are there. So going back to the reaction which we see now, we see that this entire reaction is balanced by the system which is present here, where the H2O is taken on the left hand side and OH minus systems are taken on the right hand side for the sake of balancing. So this is how the overall balancing systems takes place. Now one thing we have to understand here is that in basic medium, while in acidic medium we had this conversions, MnO4 minus were getting converted into Mn2 plus, this was in acidic medium. Whereas in basic medium, the conversions are going to be MnO4 minus converting to manganese dioxide. So this is the conversion that you are going to see in basic medium, which means that this is +7 state, this is +4 state, because O2 is -4, my oxygen is -2 into 2. So here the conversion is going to be +7 to +4. Whereas here the conversion is going to be +7 to +2. So how do we employ this concept here for this system now? Please note that the conversion earlier reaction was converting from I minus to IO3 minus. This was for the acidic medium, which as of now I am not taking it. So I am now talking about the basic medium which is present. So when I use this conversion, I have already seen that this is -1, this is +5. So what has happened here is, in this case it has lost 6 electrons, -1 to +5 is a loss of 6 electrons which is present. What has happened here? +7 to +4 means that it has taken in 3 electrons for this case. So writing this reaction for our understanding now, I minus is giving rise to IO3 minus plus 6 electrons, whereas MnO4 minus is taking 3 electrons to form MnO2, because the change of oxidation is from +7 to +4 state. So when I try to balance this reaction now, I minus plus MnO4 minus, this factor needs to be balanced now, because same number of electrons have to be cancelled. So what can I do here? I can just multiply this entire reaction by 2. So once I multiply this entire reaction, electrons will be cancelled out. So this I can take it up now as plus 2 MnO4 minus, whereas on the right hand side I have IO3 minus plus 2 MnO2. So how is the balancing conditions now? We have to take H2O on the left hand side, OH minus on the right hand side. So once we do that work, we will get the overall balanced reaction H2O and OH minus. Just count the number of atoms on the either sides now. Iodine, there is just one on either side. Manganese, there are two on either sides. What about the hydrogen? Hydrogen, there are two here, whereas there it is one. Whereas oxygen, here it is 9, 8 plus 1, 9. Whereas here it is 4, 5, 6, 7 and 8. So once you see the overall balancing reaction, you are now going to see that they have balanced this aspect with 2 OH minus, which is present in this case. So this is how the oxidation by KMnO4 takes place in basic medium. Remember that one important point in this is that whenever we take the oxidation by this KMnO4, the conversion is from MnO4 minus to MnO2. And whenever we balance the reaction, water is taken on the left hand side, whereas OH minus is taken on the right hand side. So this is the entire study of this potassium permanganate systems which we consider. So having seen a couple of oxidizing reagents, let us look at some questions which you can try out on your own and see to it that you have revised this entire part. The first question states, write the equations involved in the manufacture of potassium dichromate. It involves 3 steps. So go back, remember how the fusion process had happened, how there was a conversion from a chromate salt to dichromate salt, and then finally obtaining potassium dichromate. Mention the ore used to obtain potassium permanganate. So we have already discussed about the ores that were used for potassium dichromate as well as potassium permanganate. Mention any example of oxidizing reaction of potassium permanganate. So since I have not specified whether it is acidic medium or basic medium, you can give any example of your choice. And finally, what is the oxidation state of chromium in potassium dichromate? We have seen the calculations. So in K2Cr2O7, what is the state of Cr? That is what you need to find out for that. So this is all that we have for this oxidizing property of potassium permanganate. Thank you. Sai Ram.